Alright, hello and welcome. This is going to be our lecture video for March 31st. I'm going to be talking about just a few more concepts in Trig here and getting into graphing just a little bit. Alright, first question, draw a little sketch of this, and then we want to find x if we know that the area of the shaded region is 18 pi square centimeters. All right, so we know this right here is 18 pi centimeters squared. We're going to figure out x. So how we're going to do that is by working backwards through our sector area formula. So the sector area formula says take your angle theta divided by 360 and then multiply that, because that's the fraction of the circle that's shaded, by the area of the whole circle, which is pi r squared. All right, and this here gives us the sector area. Now let's fill in what we know. We know that theta is 80 degrees. We're going to replace r with x, because that's the variable that's being used for the radius here. And we know that the total area is 18 pi square centimeters. All right, let's solve for x. I can just cancel out the pi from both sides. With this fraction here, I could cancel out the 0, make it 8 over 36, which could then be simplified further, but I'm just going to do it in my calculator. 8 over 36, and then hit math, enter to turn it back into the fraction, 2 over 9. So 2 over 9, x squared equals 18. To get rid of a fractional coefficient, you can multiply by its reciprocal, so multiply by 9 over 2, multiply by 9 over 2, and I get x squared equals 18 times 9 over 2. X squared equals, I'm just going to do this one in my calculator too, 18 times 9 over 2, 81. And then take the square root, to get that x equals 9, but then we refer back to the problem to get the units. This is a length. The area was in square centimeters, so x must be 9 centimeters. Okay, another one, we're trying to find the angle AOB right here, that angle right in there. How are we going to do that? Well, we have the arc length, so it's 4.2 if we walked along the circumference of the circle here from point A to point B. So this curved line is 4.2, and we know the radius is 4. So what we're going to do is use our arc length formula. Arc length formula is that arc length S equals r theta. And the only trick to this formula is that it will always give you theta in radians. So I know 4.2 equals 4 times theta. Divide both sides by 4, and I get, let me do this calculator, 4.2 divided by 4, 1.05 equals theta. And that's radians. 1.05 radians. So we're done, but I think it could be useful to convert that to degrees, since half the time we like to work in degrees, half the time we like to work in radians. So what I have to do is multiply that by 180 over pi. That way I put radians on the top over here, and on the bottom over here, so they cancel out. And now degrees is on top, so that becomes my new unit. So I'm just going to do this in my calculator, 1.05 times pi, no, not times pi, times 180, divide that by pi, and I get approximately 60.16 degrees. And I like converting it to degrees here because I've got better intuition about degrees. That looks like it's about a 60-degree angle. So I feel like I've done the problem correctly. All right, our goal today is to review arc length and exact trig and to graph basic sine, cosine, and tangent graphs. Why are we doing this? To add another type of function to our graphing repertoire so that when we're doing regressions, we just have another possible graph that we can use to represent the data that we're seeing. I really want you to understand why the graphs look the way that they do by zeroing in on a bunch of examples at the key values of 0, 90, 180, 270, and 360 degrees. Okay, so my first question, based on these formulas that we learned in the last video, is it possible to get an undefined trig value? Is it possible to take the sine, cosine, or tangent of an angle and get undefined as your answer? Well, with cosine and sine, it doesn't look possible because the ratio is always some side length divided by the radius. So it's either the adjacent here with cosine, and when the radius is 1, then it's just the x value at that angle on the unit circle. With sine, it's the opposite being divided by that radius. Again, the radius is never going to be 0 though. But tangent has a different definition. Tangent is opposite over adjacent, and it is possible for the adjacent, which would be the x value in the unit circle, to be equal to 0. So this can be 0. And up here, that's fine. That just means that the cosine of that angle is equal to 0. But here, if our x value is 0, this would make us divide by 0. And tangent would be undefined. All right, and we'll see exactly what the angle is that makes tangent undefined here in just a second. All right, let's practice a little bit more exact trig with these problems here. I want to find the tangent of 390 degrees. So sometimes this is how the problem looks on your worksheet. It says tangent of theta up here and then gives you a diagram. What it's asking is find tangent of 390 degrees. It's this angle here goes and fills in for that theta. So tangent of 390 degrees. So we don't care how we got to this terminal side. We just care where in the plane this terminal side ends up being. So what we want to do to find this is put a point far out on that terminal side. And then we drop a line, like an anchor, straight down to our x-axis. All right, this constructs a right triangle, because if we go straight to the x-axis, if you go straight there, the shortest path will always make a right angle. But what kind of special triangle did we just make? Well, we got to look at the 390. It was 360 to get to right here. That was to 360. So the remaining rotation left must be 30 degrees, meaning this interior angle here is 30. And we're sort of at a place with trig where if it looks like a 30-degree angle, it probably is. That's our shortest, a pretty narrow angle, so it's probably a 30. All right, and then this up here has to be 60 because the interior angles need to add to 180. Now we got to label this with the side lengths that we've memorized for a 30, 60, 90 triangle. 1, 2, and the square root of 3. Then we label again with the words opposite. Opposite is always the up or down part farthest away from the origin. Adjacent, which is always the length along the x-axis. And hypotenuse, which is always the length of that terminal side. Now we reference SOHCAHTOA. All right, we see that it asked for tangent. So you can put a little box around the TOA part of SOHCAHTOA, meaning that we want opposite over adjacent. look at what we labeled opposite, look at what we labeled adjacent. That becomes 1 over root 3. I don't like the radical in the denominator there, so I multiply by root 3 over root 3. And I get square root of 3 over 3. And that is the exact value. If you plug in tangent of 390 degrees, you'll get a decimal on your calculator. But this gives you the exact value, and it shows where it comes from. All right, cosine of negative 13 pi over 4. Let's practice this again a little bit quicker. We'll put a point out here, drop a line straight to the x-axis, forming a right angle with the x-axis. And this is forming a 45, 45, 90. I know it's 45, 45, 90, partially just because it looks like it is. That looks like a 45-degree angle. 45 degrees are always pi over 4 multiples. So this is a multiple of pi over 4. So that's another good sign that this is a 45 degree. And if we counted it out, we would see that we had a pi over 4 remaining for this rotation, which is 45 degrees. Okay, let's label the side lengths. It's going to be 1, 1, and the square root of 2. But there's a trick here. This one down here is actually negative because we came left from the origin to get there. So that's actually a length of negative 1 when it's oriented in the plane. All right, let's go back to SOHCAHTOA. This time I want the ka part. I guess I better label these first. Opposite, adjacent, hypotenuse. I want the ka part, so I want adjacent over hypotenuse. Well, adjacent is negative 1. Hypotenuse is the square root of 2 multiplied by root 2 over root 2 to get negative root 2 over 2. Final answer there. And we can always double check with our all students take calc diagram to make sure we got the right sign. In this quadrant here, everything's supposed to be positive. We did get a positive answer. In this quadrant here, only sine should be positive, therefore cosine should be negative, and we did get a negative answer. Okay, here are some slightly trickier ones. What if we stop exactly along one of these lines? How do we still make our triangle? Because what I said is you want to always drop a line straight down to the x-axis. If I do that, I'm not going to make much of a triangle. So what I'm going to do is I'm going to take that terminal side and I'm going to move it just slightly off of the y-axis there. All right, so this is just so I can see it. It still is just right along that y-axis. I'm just opening it up so I can turn this into a flat triangle. All right, I put a point out on that terminal side and drop my anchor back down to the x-axis. All right, this length here is still 0 units. It's, just because I've pulled it off of the y-axis doesn't mean that I've made that length 0. The hypotenuse is 1, and the opposite is 1. All right, this is the special triangle I taught you guys about a couple days ago, the 90-90-0. But we can still use it to fill in SOHCAHTOA. It just happens that the opposite and the hypotenuse are now the same length. So this is still my opposite over here. This is still my hypotenuse. This is still my adjacent. And when I go to do sine of 90 degrees, I want opposite over hypotenuse. I want 1 over 1, which just equals 1. And if we plug in sine of 90 degrees in our calculator, you will see that we get 1. All right, what about if we end down here? Well, we're going to use that same technique. Pull that terminal side off of the y-axis just a little bit. You can go to either side. Doesn't matter. Make a very skinny triangle. Try to make that side straighter. Okay, and then this has a 90, a 90, and a 0. The hypotenuse is always 1, but this opposite is actually negative 1. The hypotenuse is always measured from the origin out, but the opposite is measured in the direction that it moves in the plane. So if it goes down, that's actually a negative 1. and 0 for the adjacent there. So that's my opposite, that's my hypotenuse, that's my adjacent. For cosine, I need ca. So the cosine of 990 degrees equals adjacent over hypotenuse equals 0 over 1 equals 0. All right, and these ones that end up right along the axes, you can still use. All students take calc to double check them. It's just a little bit more tricky. So right here, I'm going from all to just sine. So sine stays positive, so it makes sense that it would be a positive 1 here. Here, I go from tangent being positive and cosine being negative to just cosine being positive. So cosine is moving from being negative to positive, so it makes sense why it would be 0. All right, what if you're just asked tangent of 180 without the diagram? Well, you got to draw the diagram. So put your initial side right along the x-axis, basically invisible. Terminal side right along the x-axis going this way, but I'm going to be kind of sloppy with this one. So that's supposed to be 180 degrees right there, but I kind of got a little bit sloppy. I left a little bit of a gap, but that's so that I can turn this into one of my special triangles. Now this time that we're along the 180, now all of a sudden our opposite is equal to 0 units. Our adjacent is -1 units. Because again, it's measuring going this way. Hypotenuse always positive at 1. Tangent is equal to opposite over adjacent. Opposite is 0, adjacent is -1, 0 divided by -1 is 0. Okay, a few more. Sine of 0, cosine of 0. Let's draw that one. That would be a flat triangle over here. 0, 1, and 1 for hypotenuse, adjacent, and opposite. Sine is opposite over hypotenuse equals 0. Cosine is adjacent over hypotenuse equals 1. All right, sine of 90 degrees. There's my flat triangle, 0, 1, 1. Opposite over hypotenuse is 1 over 1 equals 1. Okay. Let's practice even more, but let's just do all of the angles that follow our axes, and we'll do sine, cosine, and tangent for all of them. So create this table. And just pause my video real quick here. Okay, so let's, now that you've drawn this table, we will sketch the flat triangle at each of these markers. So at 0, we've got the flat triangle that's going right along that positive x-axis. At 90, it's this tall triangle here. 180, flat triangle going this way. 270, flat triangle coming down here. You can draw it on either side. And then 360, well, we're back to this same flat triangle coming out this direction. Make this one a little better. Okay, and now let's label side length. So opposite is 0, 1 and 1. This one opposite is 1, hypotenuse is 1, that's 0. This one, hypotenuse always 1, adjacent -1, opposite 0. 0, -1 and 1, and then we're back to the 1, 1, 0. All right, sine, opposite over hypotenuse. So 0 over 1, sine of 0 degrees is 0. So these are all degrees. Missing our degree markers. Add those in. All right, let's look at this one. Opposite is 1, hypotenuse is 1, so 1 over 1 equals 1. Opposite is 0, hypotenuse is 1, so 0 over 1 equals 0. Opposite is -1, hypotenuse is 1, so -1 over 1 equals -1, and then we're back to a matching one here, so we're back to 0. All right, cosine does something slightly different. So because it's picking a different ratio, this one is 1 over 1 or 1. This one is 0 over 1 or 0. This one -1 over 1 or -1. 0 over 1 or 0, and then we're back to 1. So I think actually if I erased this, you would maybe see the pattern a little bit better. That it's a very similar pattern, but kind of just offset by 1. 0, 1, 0, -1, 0, 1, 0, -1, 0, 1. But then tangent is kind of different. So let's find the tangent. So this was adjacent over hypotenuse. Now we've got to find opposite over adjacent. So opposite is 0, adjacent is 1. So this is just 0. At 90 degrees, opposite is 1. Adjacent is 0, so 1 divided by 0, this one is undefined. So this tangent of 90 is one of the few trig functions that gives you undefined. All right, let's keep going. Opposite 0 over adjacent -1, we get back to 0. Opposite over adjacent, we get another. This one is -1 over 0, but it's still undefined. And then we're back to 0, so the pattern repeats. We're at 0. So if I count by 90s, tangent goes 0, undefined, 0, undefined, 0, undefined, and on and on. Okay, but this is every single tricky flat triangle problem. I don't recommend trying to memorize this table, but just realize that there aren't that many out there that can be all that tricky. Okay, we're going to call that good for this video, and then I'm going to pick it up on the next video where we're going to graph the basic shape of sine, cosine, and tangent.